Today we are going to do simple harmonic motion. If you consider the oscillation of a pendulum, in a pendulum, the bob is moving in a certain direction, but gravity, the component of gravity is trying to pull the bob back to its rest position. So the force on the bob is directed oppositely to the displacement, or you can say that the acceleration of the bob is proportional to the displacement and directed oppositely. So this type of motion is called simple harmonic motion. So simple harmonic motion is any oscillatory motion in which the force and displacement are proportional and the direction is opposite. So suppose we are discussing a simple harmonic motion. So acceleration is proportional to minus x. So acceleration is minus omega square x. So F is equal to ma is equal to minus m omega square x is equal to minus kx. So acceleration is proportional to displacement. The constant of proportionality is minus omega square, and we know force is ma, so we write it in this manner. So we can now say that m omega square is k. So omega is equal to root over k by m. So this will be the angular velocity, that is omega is equal to root over k by m. Now the equations which we have got, these equations are not giving us any instantaneous expression for displacement. So what we will do is we will now try and develop expression for instantaneous displacement. So acceleration is minus omega square x. So we can say that v into dv by dx is equal to minus omega square x. So v dv is minus omega square x. Now you integrate both sides. So this will become v0 square, v square by 2 minus v0 square by 2. So this is what we get. So this is the expression for velocity. Now suppose we put v0 square by omega square plus x0 square is a square, then we are getting one result. V is equal to omega into root over a square minus x square. Once again, incidentally, this is also a very important result. So I am calling it as 1. Now, if we write dx by dt is omega root a square minus x square, then this is what we will get. Now let us integrate both sides. So after integration, we will get sin inverse x by a is equal to omega t. So sin inverse x by a minus sin inverse x0 by a is omega t. So this gives us x is equal to a sin omega t plus delta. So this is equation number 2. Now, if you differentiate both sides, then V is a omega cos omega t plus delta, and acceleration is minus a omega square sine omega t plus delta. So we have basically come back to our original equation, that is acceleration is minus omega square x. So these are the four basic equations of simple harmonic motion. Velocity in terms of x, x in terms of t, v in terms of t, acceleration in terms of t, and acceleration in terms of x. A is called the amplitude of simple harmonic motion. Then omega is called the angular frequency. And delta is called the phase constant. For example, at t equal to 0, if x is also 0, then delta is 0. So that means the particle is beginning the simple harmonic motion from the mean position. On the other hand, at t equal to 0, If x is equal to a, then delta is pi by 2. That means the particle is starting the journey from the extreme position. T is the time period of simple harmonic motion, and the value of t is 2 pi by omega. So the time period of simple harmonic motion is 2 pi by omega, which can also be written as 2 pi into root m by k. Okay, now we come to energy of simple harmonic motion. First is kinetic energy. So half m into a omega cos omega t plus delta whole square. So it is half m a square omega square into cos square omega t plus delta. This is the expression for the kinetic energy. Now, suppose I want to know what is the maximum kinetic energy. So maximum kinetic energy will happen when cos square omega t plus delta is 1. So maximum kinetic energy is this, which means the total energy is this. And potential energy is total energy minus kinetic energy. So this is the calculation. So half m a square omega square into sine square omega t plus delta. So this is the formula for kinetic energy, and this is the formula for potential energy, and this is the formula for total energy. So these are the formulas to find the energy of SHM. Okay, now we come to the simple pendulum. Now in a simple pendulum, the component of gravity perpendicular to the motion is g sine theta. Now, so we can say that acceleration is minus g sine theta because the bob is traveling this way and the gravity component is acting the opposite way. Now, if theta is a small angle, sine theta is approximately equal to theta, and we can say that that is minus g into x by L. So that is minus omega square x. So omega is root over g by L. So time period is 2 pi into root over L by g. So this is the formula to find the time period. Now there is another way to analyze SHM. Whatever we have been doing just now, that is called linear SHM. So there is another way of studying SHM, that is known as angular SHM. In linear SHM, x is a sine omega t plus delta, and here theta is theta 0 sine omega t plus delta. V is a omega cos omega t plus delta. Omega is theta 0 omega cos omega t plus delta. Acceleration is minus a omega square sine omega t plus delta. Alpha is minus theta 0 omega square sine omega t plus delta. Omega is equal to root over k by m. Here omega is equal to root over k by I. Here f is equal to minus kx, and here torque is equal to minus k theta. So whatever formulas we have discussed till now, they fall under the category of linear simple harmonic motion, but you can also have corresponding formulas for angular simple harmonic motion. Let us go back to the pendulum. Suppose we say that OA is the axis of rotation, then the torque about the axis of rotation is equal to mg into L sine theta. In fact, minus mg into L sine theta because the torque is restoring in nature. So that is coming minus mgl into theta. Now we know that torque is equal to minus k into theta, or we can say I alpha is minus mgl into theta. So alpha is minus mgl by I into theta. And I you can easily see from the figure that it is ml square. So alpha is minus g by l into theta. So time period is again coming the same formula, 2 pi into root L by z. Then we come to physical pendulum. In a physical pendulum, instead of a string and a bob, we have a body in which O is the suspension point, mg is the weight of the body, OA is the axis of rotation. Now, the torque of mg about OA is mg minus mg into L sin theta. So I alpha is minus mg into L sin theta. And if we take sin theta approximately equal to theta, this is the equation. So omega is root over mgl by I. Next we come to torsional pendulum. Basically this is a wire which is capable of sustaining a twist. Suppose the angle of twist is theta. So we know that torque is equal to I alpha. It is equal to minus k theta, where k is called torsion constant. K is called the torsion constant. So this is the expression which we are getting. So omega is coming root over k by I. So time period is coming root over 2 pi root over I by k. Next we come to combination of SHMs. So this is x1, this is x2, so the combination of these two SHMs, the formula is x1 plus x2 is a sine omega t plus epsilon. So A is given by root over a1 square plus a2 square plus 2a1 a2 cos delta, and tan epsilon is given by a2 sine delta, where a is root over a1 square plus a2 square plus 2a1 a2 cos delta, and tan epsilon is a2 sine delta by a1 plus a2 cos delta. So this is the topic combination of SHMs, and this brings us to an end of the chapter simple harmonic motion, and also the end of this session.